Brown, and today it's basic terms. There are a number of words and phrases which are common to many areas of industry, and today we're going to discuss several of these. First, we'll pick a few words at random. For example, force. Force is what this box, which weighs 50 pounds, exerts on the table. That is, 50 pounds force downward. And when the young lady tries to lift it, she's downward. And when the young lady tries to lift it, she's exerting force upward. Okay, now let's get one more definition. Work. Work equals force times a distance. Now remember, this is a definition which has been assigned to work. Now box. By definition, no work has been done on it until it moves. Now if it is lifted 1 foot, since it weighs 50 pounds, we have 50 times 1 foot equals 50 foot-pounds. So work equals force times distance and can be measured in foot-pounds. Torque is probably a new term, but it is one to remember. It's the twist in a shaft that has one end fixed and to which a twisting force is applied. It is also measured in foot-pounds. Here, a foot-pound is a measure of twist that will be produced in a shaft by the leverage of a lever 1 foot long, which has 1 pound of force applied to the end of it. If we take a wrench 1 foot long and put it on this motor shaft, when the motor starts, the number of pounds at the end of the wrench will be a measure in foot-pounds of the torque that the motor will develop. Okay, let's try it. We hook a spring scale onto the wrench at 1 foot from the shaft. The wrench is the lever arm, and we start the motor. Now, as you can see on this 10-pound scale, the scale reads approximately 7 pounds. This, then, is the motor's starting torque, 7 foot-pounds. To convert this to inch-pounds, all we have to do is multiply by 12. That is, 12 inches per foot. So many pounds at so many inches lever arm. Since the shaft isn't turning, this is static torque. The next formula, beyond the one for work, includes the factor of time. It is stated power equals work done for a period of time. In a shaft that is turning, torque is a measure of power and is per minute, or RPM. Here we have force in foot-pounds times distance, revolutions at 1 foot lever arm, times time, 1 minute. A good fact to remember for quick calculations is that a torque of 3 foot-pounds at 1750 RPM equals approximately 1 horsepower. Horsepower, or HP, is another way of measuring power. 1750 RPM is the most common speed of an electric motor. Since torque is twist in a shaft, if we put some sort of slip clutch into the system, such as this one, it is called a torque limiter. Theoretically, a mechanical horsepower is 1 1/2 times the amount of work that an average horse can do continuously. James Watt came up with this definition as a way to rate the power output of his steam engines, and I've often wondered how he decided what was an average horse. But anyway, he defined mechanical horsepower as the amount of work done in lifting 33,000 pounds 1 foot in 1 minute, or 1 pound 33,000 feet in 1 minute, 33,000 feet in 1 minute, or any combination which would equal 33,000 foot-pounds per minute. Electrical power is measured in watts. Expressed in electrical terms, 1 horsepower, or 1 HP, equals 746 watts. Now 1,000 watts equal 1 kilowatt, or kW. So 1 horsepower equals 0.746 kW, or kilowatt, is another fact to remember for quick calculations. 1 horsepower equals approximately 3/4 kilowatt. There's a problem which comes up relatively frequently: how to determine RPM of a driven unit. And there are a couple of easy ways if you have the proper equipment and the unit is accessible. First, there is a unit which is known as a tachometer, which operates something like the speedometer on your car. It reads directly in RPM, as you see here. Next, there's the strobe tack, which is a relatively new item, but it electronically counts the reflections per minute from a piece of tape, which has been put on a turning unit. But what if you don't have a tachometer? Okay, usually the motor has a nameplate, which will tell its RPM. If the pulley or sprockets on both the driver and the driven have the same diameter, that's the distance from here to here, are the same, then the driven speed will be the same as the driver's speed. But what if we have a situation like this, where the diameter of the driver is 3 inches and the driven is 6 inches? Okay, now we have a formula. Driven speed equals driver diameter divided by driven diameter times, so we would have driven speed equals 3/6 times driver speed, or driven speed equals 1/2 driver speed. It should be noted here that when the term diameter is used, we are actually talking about pitch diameter, which is from a point from the middle of the belt to the middle of the belt on the opposite side of the pulley. While you will probably not be able to measure pitch diameter exactly, you will be able to be close enough for most applications. If you're using a chain drive, then you only have to count the number of teeth on the driver and the driven. Our formula now becomes driven speed equals number of teeth on the driver divided by number of teeth on the driven times driver's teeth on the driven times driver's speed. If you should become confused as to which goes on top and which on the bottom in the formula, just remember that the larger diameter, the sprocket or pulley with the larger diameter, will always turn slower than the smaller one. So if your answer comes out with the large pulley turning faster, then you'll know you've made a mistake. Pure iron is relatively useless in industry, while cast steel are extremely important. The only difference in pure iron and steel is the carbon content. Cast iron usually ranges 2.5 to 5% carbon, while steel is in the range of 0.05% for certain low-carbon steels to as high as 1.25% for razor blade steel. Cast iron is relatively resistant to corrosion, tends to dampen vibration, is easily castable, and its machinability varies with its hardness. It has relatively low tensile strength, which means a bar will pull apart relatively easily as compared to steel. It will take high loading when it's being pressed on, such as base plates on a press. It is not ductile at all, which means it won't bend or can't be formed. Malleable iron is cast iron which has been heat treated, and as a consequence has many of the properties found in steel. It is ductile, it has a relatively high tensile strength, and is the easiest to machine of all of like properties. Malleable iron is widely used for pipe fittings and many cast chains used in industry. Ductile iron, or nodular iron, is a relatively new type of cast iron. By the addition of small amounts of alloying materials and special processing during melting, a material is produced which is about halfway between steel and cast iron, with many of the desirable properties of each. Carbon steel has a wide range of properties depending upon its carbon content. The main difference in the steel in this wire and the steel in this razor blade is carbon content. The more carbon a steel has, the less ductile it tends to be, and the harder it can be made with proper heat treatment. Stainless steels are alloys or combinations of steel and one or more additional properties which were mixed while melted. Nickel and chromium are two of the more common alloying metals. However, several others are used depending on the required properties of the alloy. Heat treatment. Heat treatment is a method of changing the physical properties of metal, usually to make it either harder or softer. The metal is heated up to some temperature less than its melting. How long it is left at that temperature and how rapidly it is cooled will help determine its final properties. If it is chilled quickly, such as by placing it in oil or water or some other medium, the process is called quenching. Each particular metal or alloy has its own heat treating procedure. For example, carbon steel is hardened by heating and then quenching, while copper is made soft. The same process. Heat treatment is also used to relieve stresses in metal. Stresses in metal are internal forces which tend to make the material unstable. For example, a piece of cast iron which is welded may have such high stresses set up in it that it may crack as it cools. If, however, the cast iron is heated up before welding, called preheating, and it is heat treated, that is, it is predetermined temperature after welding and then slowly cooled, the stresses are relieved and it won't crack. Of course, as in all welding, a welding rod suitable to the material being welded must be used. Welding is the process of joining two pieces of metal together, usually by melting the edges of both the pieces to be joined. This is usually accomplished with a welding rod through which we pass an electrical current which makes an electric arc melts the two edges to be joined. Usually a filler or welding rod is used so that the final weld normally has a raised surface. This melting can also be done with an oxyacetylene torch like this, which uses a mixture of oxygen and acetylene. Joints of lesser strength can be made with filler rods called solder, which are alloys which melt at a temperature less than that of the two materials to be joined. In solder, to be joined are not melted. They are instead coated or wetted, as it is called, with the molten solder, and the two parts are joined while the solder is molten and allowed to cool. This joint then is only as strong as the soldering material. There are three basic types of solder. First, there is soft solder, which is used on things like electrical connections, copper plumbing fittings, and sheet metal work. It is an alloy of lead and tin and melts 360 degrees Fahrenheit. Next is silver solder, which is an alloy of silver, copper, and zinc. And it melts at a temperature of approximately 1250 to 1600 degrees, depending upon the alloy used. Silver solder is widely used in refrigeration work and in the jewelry trade. It makes a relatively strong joint and is frequently used in different metals together. The third method of soldering is called brazing. Brazing is identical to silver soldering, except the solder is usually a brass rod, which means it's an alloy of copper, zinc, and sometimes small quantities of other metals. When either welding or soldering, the two parts to be joined must be cleaned, and a flux is usually also required. Flux is a substance used to prevent oxidation of the hot metal surface and to help clean it of any present. Oxidation of steel is called rust. A variety of materials are used as a flux, depending upon the work to be done and the particular kind of solder used. Elastic limit is a way of defining in terms of unit loading the extent to which a material will stretch or bend and not be permanently deformed. Unit loading means so much load applied to so much area. The load is usually in pounds, is usually a square inch. Thus, if we have 1,000 pounds load applied to 4 square inches area, then the unit loading would be 1,000 divided by 4 equals 250 pounds per square inch, or 250 psi, as it may be shortened to. If we had 1,000 pounds applied to an area of 1 inch, the unit loading would be 1,000 divided by 1,000 psi. This is the force on a part of 1 inch cross-section. And what is the cross-section? If you can imagine this stick of margarine as being a piece of steel 1 inch square, then its cross-section would be right here, a section across the material. As you see, this spring can be loaded or stressed and will repeat this cycle as long as we do not exceed the elastic limit. But if we stress it beyond the elastic limit, like this, then it won't return to its original position. Yield point is the point at which there is an appreciable increase in deformation without any additional load. For most ductile materials, that is, any material that can be easily bent or formed, the elastic limit and yield point are very nearly the same, and they're sometimes used interchangeably, although once again, the loading is normally expressed in terms of pounds per square inch. Ultimate strength is the most loading a material can be subjected to before it fails. Working strength is the unit loading at which experience has shown the material can reasonably be expected to serve for its design life. Working experience has shown the material can reasonably be expected to serve for its design life. Working strength, or working stress as it is usually called, is always considerably less than either ultimate strength or yield strength. The ratio between the two, that is, ultimate to working, load may run as high as 10 to 1 or more. This ratio, then, is what is known as a safety factor, or it is sometimes called service or experience factor. Through the years, experience has shown that for a certain kind of service, a certain safety factor will have to be used if the unit is to perform satisfactorily. In some applications, ultimate strength is the limiting factor, while in others, yield strength is. So hence the two different formulas. Fatigue break caused by repeated application and release or reversal of a load which does not exceed the elastic limit. That is, no permanent deformation